Hello and welcome to another Clinical AI Grand Round. I'm Dr. Coates. The topic today is supervised, unsupervised, and reinforcement learning. As always, let's begin with the why. The fear-based reason is job displacement. AI will transform healthcare and will displace some of our roles. The positive reason is we can translate our deep knowledge of medicine into the AI field and thrive in the new economy. So let's get going with an illustration. Meet the Rhythms family. The Rhythms are a very medical family. The parents, Ali and Gora, have 3 children, Una 32, Roli 27 and Supreet 20. Supreet is in his 2nd year of medical school. Roli has just started core surgical training as a resident. Una is senior resident in the emergency department. Supreet is a supervised learner. His medical school tutors give him vast amounts of information. For example, he has learnt all the symptoms and signs of a heart attack. In this example, the symptoms and signs are inputs and can be represented by X. The diagnosis is the output and is represented by Y. His college supervisor has spoon-fed him the features of every pattern. For example, male, over 60, smoker, chest pain into his left arm, tachycardia, ST elevation on ECG. This is a heart attack. So Supreet is given both X and Y and is supervised to learn F, the model or pattern of disease. At the end of term, Supreet sits a national exam. He is presented with 50 questions, in which he is given signs and symptoms and asked to offer a diagnosis. He is able to offer the correct diagnosis in 40 of the 50 questions and scores 80%. He is considered a good learner. His college supervisor feels validated and vindicated. The training is clearly of a good standard because his class performance metrics are good. The college is turning out good learners who, when faced with new inputs, can use the disease models they have learned to come up with correct predictions. To summarize, Supreet is an example of a trained and validated supervised learner. After he qualifies, we will think about his post-training performance and its generalizability. Did targeted medical school training prepare him for the general practice of medicine and surgery? As he progresses, he may take postgraduate medical exams to fine-tune his skill in a particular specialty. Now let's move on to Una, our unsupervised learner. Una is 32 and is a senior emergency department resident. She will soon be a consultant and loves doing a challenging take in the ED. Patients walk in with all sorts of problems that she has to triage to an inpatient specialty. In this example, both the inputs and outputs are unsorted and unlabeled. Una applies the pattern recognition she has learned over the years to the unsorted take. Her key skill is clustering. She is able to reduce a large pool of unsorted patients to manageable dimensions. First, she sorts patients by age. Anyone under 16 goes to pediatrics. Anyone over 70 goes to geriatrics, unless they have a limb injury. The men under 40 are referred to trauma if their leg is sore, and referred to plastics if their hand is sore. Men over 40 are referred to the medics. And so on and so forth. Una is an example of an unsupervised learner. With years of experience, she can spot patterns. These patterns are agnostic to patient symptoms, signs and diagnoses. She has unlabeled inputs, X, and unlabeled outputs, Y. However, she has learned F. Una has a pretty good classification hit rate. Her post-training performance is high. For example, when the geriatric registrar comes down to see the patients she has sent to geriatrics, he makes a relevant diagnosis in 8 out of every 10 patients. Lastly, we have Roli, who is a reinforcement learner. He just about made it through medical school. He was never one for long library hours. However, he has discovered surgery and suddenly, everything makes sense. In theatre, he is in flow. He watches the professor perform an operation and learns all the possible ways to execute a particular task. When he finally gets to try the task himself, he is always happy to get feedback. When he gets shouted at for sloppy knots, he quickly adjusts his method. When he gets praise for a particularly good skin closure, he knows he is on the right track. Rowley is an example of a reinforcement learner. He learns through trial and error. He has a simple formula or value system. At each step, he seeks to maximize his reward, the professor's praise, and minimize cost, the professor's scorn. By thinking about algorithms as a family of machine learning methods, we can now appreciate each of the learning style of these algorithmic children. We can also see that an unsupervised learner represents a level of sophistication where the training inputs are now well embedded and the learner is able to grow beyond their training, to take on unlabeled and unsorted data environments. In practice, the question being asked and the data environment will determine which algorithm is applied. Similarly, the learning styles of the algorithmic children means that they might thrive in one environment and flounder in another. For supervised machine learners, tasks they excel at will generally be regression and classification. Unsupervised machine learners excel at clustering tasks and dimension reduction tasks. Reinforcement learners are useful for dynamic programming, including Markov decision processes and temporal difference methods. Focusing on reinforcement learning, let's linger over another useful analogy. Surgeons often quote the neurosurgeon John Garfield, who said, "You can teach a monkey to operate, but you can't teach a monkey when not to operate." This is quite relevant to reinforcement learning. In surgery, trial and error alone can lead to successful skill acquisition. For example, incision and drainage of an abscess. However, a wider understanding of the data environment will improve performance and shorten training. For example, understanding that an epidermoid cyst is not an abscess and should be excised rather than incised. In practice, methods are often used in combination. For example, a GPT, a generative pre-trained transformer, will be heavily supervised and trained for years on exaflops of data, then fine-tuned using reinforcement learning techniques, before being deployed into the real world to work in an unsupervised way. Indeed, some AI algorithms use these methods in combination. I hope thinking about machine learning and AI approaches through the lens of medical training is helpful. As the original learning machines, doctors ought to feel familiar and confident with these training methods. Please send in your comments for other topics you'd like discussed, and share this video with at least one other medical colleague.